Three, two, one. Hello, everyone, and welcome to Math 495. You are hearing the dulcet tones of Professor Christopher Lee, your instructor for this course. All right. So as per the announcement, for the first day of class, not in person, previously recorded, posted. At the end of the day on Wednesday, not before actual class time. As noted, we were in Iowa City for a doctor's appointment. Hopefully should be the only one for the semester. Start face-to-face instruction on Friday, and we should be good to go from there. But yeah, so for the purpose of this video, just some basic stuff. I want to go over the syllabus briefly, and then kind of do a brief little introduction to what the course is going to be about, what we're going to be focusing on. Yeah, and all that good stuff. Alright, so let's get into it with the syllabus, which is available on Canvas if you have not found it yet. Alright, so this is special topics, so we're getting into the habit here of running a special topics every semester. And this special topic course that you sign up for is chaos and fractals. So chaos and fractals is a subject in mathematics that I hold very near and dear to my heart. A little bit more on why in a little bit, but a little background on this. This actually used to be a class here. This was Math 439. And basically, nobody ever signed up for it, so it just got deleted. But the last time it was offered, I taught it. So this is, once we started doing the special topics thing, I'm like, yo, I'm doing my chaos fractals class. So that's kind of the story of why this class exists. Alright, so again, I don't think I need to fully introduce myself, as I think everybody signed up for this class has had me before, so that's a good time. It's good stuff. But anyway, if you don't remember, Professor Lee, my office is in the math office, 396. There's my email, the best way to contact me. Please give me at least 24 hours to respond to any emails. I'll do my best, but, you know. We try. I haven't figured out my office hours just yet. This will be updated, and I'll let you know. But also, of course, any time we can make a WebEx work, I will willingly do that. All right. So, as already noted, the course will be face-to-face. This should hopefully be the only pre-recorded thing we do. It will be in Pearson, 2143, Monday, Wednesday, Friday, and look at this, beautiful, 11:50 normal times. My other class is doing the stupid COVID start at 55 thing, which is good news, which means I'll hopefully never actually be late. I have to walk from Gilman to Pearson. It's not too bad, but still a bit of a walk. Alright, the textbook is an all-time classic in the subject. So when you talk about chaos and fractals, this book by Stephen Strogatz is probably like the book. So not only just for this course, it is, of course, where we're going to do homework from and all that other good stuff, but it's just a quintessential math book that everybody should have. So if you physically bought a copy, that's great. And obtain the book in any way. I'm not saying you should Google nonlinear dynamics of chaos PDF, and like the second link is a PDF of the book for free. I'm not saying to do that, but physical books aren't bad either. I actually own the first edition. Because actually, 14 years ago, I took this exact class that you're taking with this exact book, so, yeah. Anyway, yeah, this is an all-time classic. It's a wonderful book, and hopefully by the end of the semester you'll agree with that. Alright, so course description. So it's special topics, its actual description is like, current topics in math. But here's the description we used for Math 439. So like I said, this used to be an actual course. So we'll talk iteration of maps, classification of periodic points, bifurcation theory, chaos, fractals, and fractal dimension. And all of those will mean things to you by the end of the semester. Alright, so for a more precise breakdown of the objectives we're going to hit and the sections out of the textbook that we're going to look at, so the course will basically break down into 3 parts, one-dimensional, two-dimensional, and then chaos. So one-dimensional, we'll basically kind of be like rehashing what you did in differential equations, but we're going to come at everything from a completely different angle, and more on that in a little bit. Then we'll move on to second order, so systems of differential equations with two derivatives that we're looking at, derivative of x and the derivative of y, and studying there. Note some repeated words here: fixed points, fixed points, fixed points, bifurcations. We're going to define those things, and they're going to be our bread and butter pretty much for the entire course. And then after we finish up 2D, we then move to the world of 3D, and that's when we go chaotic, and specifically, we give the precise mathematical definition of chaotic, which is aperiodic long-term behavior in a deterministic system that exhibits sensitive dependence on initial conditions. And again, we'll make all of those words make sense when we get there. And then we will talk about fractals and fixed points of one-dimensional maps and other good stuff. Lyapunov exponents. It's a great time. I'll talk about the all-time classic fractals, the Cantor set, the Koch curve, and the Sierpinski carpet. Good stuff. Okay. Grading. Super simple. Homework, midterm, final. That's it. Here are the guarantees, the usual stuff. 90s is A's, 80s is B's, 70s is C's. You're right. You show up, you submit stuff. Yeah. Don't worry. Don't worry. I'll take care of you. You shouldn't end up down over here unless you're just not doing stuff. So, all right. So problem sets will be posted. These are going to be problems assigned out of the textbook. Typically, I'll grade them on. I'll collect them on Friday, and I won't grade all of them. I'll just randomly pick a couple and just grade those. And something I really want, since there's only like 7 of us here in the course, not including me, I really would love it for all of you to work collaboratively on these homeworks and Google stuff, research. Just make sure whatever you give me in the end is your own work. If you want to handwrite it, fine. LaTeX will be preferred, especially with some of the problems, because there'll be some. You can do some of these things by hands, but you can make a computer make the pictures look a little bit nicer. So the coding won't be a requirement for this course, but there's going to be moments where we're going to want to just write some simple code to draw some nice pictures, which we'll be seeing in a moment. All right, so we'll do a midterm and a final, and again, these are no big deal. Just let's take a break about halfway through the course and just remind ourselves of everything we learned, and then at the end of the class, just dig up everything that we learned this semester, and no heavy lifting. This is going to be a laid back class. All right, we won't have the usual stuff, homework, midterm, and final, but the stakes are low. All right, and to wrap up the syllabus here, we've got the usual stuff. So the department policies on like makeups and late stuff, and email me. Just email me and tell me what you need. I'll work with you. We'll be good. Here's the chalk paragraph. The y'all can behave. So now we got to put this in our syllabus. I am required by the university to include this now. So every time I do a syllabus, I'm always gonna be like, you idiots, you absolute dinguses. We got to do this now. I always like this, like, class context is germane to the subject matter. If you had me in class before, which is all of you, I can make anything germane, so we've definitely gotten off on some weird tangents, and this course will be no different. Alright. Okay, and then the last thing, so it's, hopefully it's over soon, but we're still hanging out with the big Rona. And when it comes to that, just the university has a moving forward webpage about kind of what's going on with that. I will be wearing a mask. I suggest you do so as well. And hopefully by the end of the semester we won't need to do that anymore, but we'll see. But anyway, so that'll be that in terms of that stuff. Hopefully this is the last time I have to include this in a syllabus, but we'll see. Alright, any questions about the syllabus, email me, or when I see you in class on Friday, ask. Alright, cool. Alright, but let's get into it. Okay, so I set up these, so my other class, IFIQ, I did an about me, and I just, copied and paste. Like I said, I think everybody in this class has had me before, but in the event you don't know what I look like, there I am. Ooh, looking I'm looking a little pudge. Feel like you look at that there. I have since our daughter Charlotte was born, I've gained like 40 pounds. So I'm feeling a little bloat these days. We'll see. But in addition to our daughter Charlotte, our daughter Olivia is also with us now. There's my wife Allison, who is a grad student in the School of Education, and she teaches ED UC 333. If I remember, yeah, I think that's the number. Not this semester. I was taking a break with that. This photo shoot was a lot of fun because this is like the only picture we got of Olivia where she wasn't like super mad, and Charlotte got a splinter somehow, and she was very upset. So it was a good time. All right. But anyway, some basic stuff about me. In the event you do not remember, I am from Long Island, New York, specifically from a place called West Islip. That is how that is pronounced. As the semester goes on, the accent sneaks in every so often, but for the most part, it's gone, I guess. So let's talk about chaos and fractals a little bit. So the school I went to, Clarkson University, which is a small engineering school up by the Canadian border in New York. The big subject there, the main thing that everybody at that school studied, was chaos and fractals. I didn't do that. I did functional analysis, but I took a lot of chaos and fractals stuff. In fact, almost every class I took was like devoted to chaos and fractals one way or the other. So a lot of my classwork was actually all this fun stuff we're talking about. I never did any research in it, but I took a lot of classes. All my buddies in grad school like studied this stuff, so I got a lot of fun, positive memories of the material. So I'm very happy to share that with all of you. And I hope you enjoyed too. And if you look at when I got my PhD, this is a special year for me. It's my 10-year anniversary of earning my doctorate. Ooh, specifically on 4/20, that's when I defended my thesis. Was very happy about that turn of events. And a little bit more of that later in the semester, maybe. I've been thinking about doing like a 10-year retrospective video on it. Because me and the same year I got my PhD, my friend Rumi got her PhD in Japan, and recently we started working on a problem together, and it's an offshoot of what basically our what we both did for our dissertation. So we got some new stuff going on. So we'll see. All right. So in addition to mathematics, the other thing that I have wasted all of my free time on, other than my family, is chess. Right, the pandemic got the chess boom going. Although, to be fair, I did do chess club in middle school, so I was kind of already mildly indoctrinated. But anyway, so I'm a big fan of the chess, and my name on the bad chess website and the good chess website is Bishop's Lemma, which is, I was very happy this wasn't taken. And in fact, so as I mentioned, my PhD was in functional analysis, and it was based off of work that a mathematician named Eric Bishop did. And in fact, we have something we call Bishop's Lemma. And so I was pretty excited that I was able to actually get that. Cool. All right. So that's the little about me. So let's get into about the course. What are we actually doing in this class? All right. So let's set the stage. Here's the story. So in 1963, a mathematician by the name of Edward Lorenz was studying the following system of differential equations. So he was looking at three equations. Excuse me. Three unknown functions, x, y, and z, and he had the following setup. The derivative of x is 10 times y minus x, the derivative of y is 28 times x, minus y minus x times z. So note, this is a system of nonlinear equations. And z prime is x times y minus 8/3 z. The 8/3 is weird, but later on in the course, when we fully investigate this, these numbers are chosen very deliberately. So Lorenz basically picked very specific numbers because he knew something was going to happen with this particular system. So in particular, so he investigated this, and now note, like I said, it's nonlinear, which means you've got no hope of actually solving this. Actually getting formulas for x, y, and z, you do not even care. You're not even going to put effort into figuring out. what those formulas would equal. Instead, you're going to do numerical approximations, and we'll talk about how you do that. But anyway, so this was kind of the heyday of like supercomputers. And so Lorenz had access to one, and he's like, yo, I've been looking at this, and I think this is going to do something wild. So he had a computer get approximate solutions for x, y, and z, and he gave it the initial condition 0, 1, 0, and he wanted to look at the trajectory x and x of t and z of t. So again, you have three functions here, x, y, and z. The independent variable for all of them is t. And so what he wanted to plot was, okay, I'm going to do x versus z, and I'm going to let t run from 0 off to as far as the computer will let me go. And I'll have the trajectory start here. So it'll start at 0, 0. The y being 1 is for reasons, which we'll get into. And he did a little work, and he was sure that what he would see would be pretty amazing, and the computer gave him this picture. Well, his computer didn't. This is the picture my computer gave me after I ran it. So if you see what's going on here, we start at 0, 0, so this is x versus z. I should have included the axes. Oops. Anyway, so it's x versus z. So it starts at 0, and when you follow the trajectory, it kind of goes up, and then it immediately flies over to here. But note that it starts kind of spiraling out. And if you follow the trajectories, eventually it spirals out and flies over here, where it then spirals around this, but gets blown away, but then eventually gets attracted back and spirals in, but then spirals out, and then this process goes on forever. So Lorenz studied that differential equation. He did not solve it. He did not figure out what x, y, and z were actually equal to. He qualitatively analyzed it, and he figured out that this is going to do something weird. And I can only imagine that when he plugged in the computer and he got this image, this was his reaction. I don't know if it was that dramatic, but I'm sure it was pretty mind-blowing seeing that, seeing as how it was the first time anybody had ever seen anything like that. So, our goal is to figure out what this shit is and why we don't need to be scared of it. Alright, but we're not going to go in all guns blazing with a system of third-dimensional, we're not going to go right in with a system of three differential equations. Let's baby steps it. We'll start off with the first order case, and specifically we'll look at differential equations of the form x prime is equal to f of x. So if you let your mind float back to differential equations. First order, there's only one derivative, autonomous, meaning that the right-hand side only depends on the unknown function x. It's not dependent on time, hence the autonomous part of it. So, again, what we want to stress here is that, again, Lorenz did not actually get formulas for x, y, and z. He instead did qualitative studying of the differential equations. Because even in your differential equations class, we spent a lot of time solving them, getting answers. And we're kind of, and again, this is like every math class you're ever going to take. Each new math class you get is going to tell you the previous math class lied to you the entire time. When it comes to differential equations, you usually can never actually solve them. Getting a formula for the solution is either incredibly hard, outright impossible, and a lot of the times it's outright useless, because even if you can solve it, the formula is probably like some jank, like multiple compositions of like square roots of sines and cosines and cube roots. It could be just a complete mess and completely worthless for what you actually want to do. So this class is going to be all about studying differential equations. For the first chunk of it, we're going to do, this is known as continuous chaos. Discrete chaos, we'll talk about later in the course, where we'll leave differential equations. Basically we're going to understand how the solutions work without ever solving them. So every equation we see in this class, we are like literally not going to actually solve. We are instead going to go, can I figure out stuff about the answer without actually getting it? So this is kind of going to be a very interesting math class, because we're going to get differential equations, and basically we're like, I don't care about solving it. I want to do these other methods to understand how they work. And yeah, it'll be good stuff. And in fact, in your differential equations course, you actually kind of did a little bit of this, not a lot. You got a little sample of it, and this course is going to be nothing but that. That being said, though, we will pull out some separable D's, linear D's. We'll bring back some of the greatest hits. And in fact, that'll be something we do on Friday. We're going to have a fun little in-class project, and it'll be good times. All right. So again, our goal is basically going to be, how do you actually extract information about how the solutions behave without actually getting them? Okay, and so the first one that we're going to address is the idea of a fixed point, also known as an equilibrium solution. So note, what is this? So if I give you a first-order autonomous differential equation, y prime is equal to f of x, a fixed point is when plugging in a constant into f gives you 0. And note, this, in other words, this is saying that the constant function is a solution to the differential equation. That's why these are also called equilibrium solutions. Now, it turns out that so note, this is kind of like you're cheaply solving the DE. You're just finding the constants that would satisfy it. It turns out that these will actually tell you a lot about the behavior of other solutions. Let's get an example to give us an idea of why that would be the case, and this will give us our first sort of sampling of why fixed points are very important and why they're usually the first thing you go after. So, side note, on the Lorentz system, it's not too hard to see that it actually has a fixed point at 0, 0, 0. Plug in all the zeros, it works. Which is why your initial condition here needed to be something other than 0, 0, 0, which is why the y was equal to 1. Alright, but here is a first-order autonomous DE, so x prime is equal to 4x squared minus 16. So again, let's remind ourselves what a diffie when you read this. This is saying, I am talking about the function whose derivative is 4 times itself squared minus 16. Okay, and now note, I cannot solve this by integrating. If I integrate, I get x on the right, left, but on the right, I get an integral. I get the integral of x squared. Now that's an integral equation, and there is a branch of math devoted to solving those. Hopefully the math part of your brain kicked in, and you're like, differential equation, I bet there's integral equations. It turns out there are, and it turns out that they're yeah, we'll leave it at that. Anyway, okay, so in this case, our f of x, the function that's on the right-hand side, is this. So I am going to go after my equilibrium solutions, my fixed points, so set it equal to 0, and just solve for x. Alright, and then here we find that this particular first-order autonomous DE has two sets of constant solutions. It's got 2 and negative 2. So these are solutions to the differential equation. They're very boring solutions, but they're solutions. Now, let's analyze them a bit closer, because it turns out, with these in mind, I can actually tell you something about how all of the solutions to this differential equation are going to behave, because these fixed points, these equilibrium solutions, basically exert their influence on the other solutions that are out there. Alright, so when x is less than negative 2, if we look at our differential equation, we'll see that the derivative is positive. When x is between negative 2 and 2, we see that the derivative is negative, so that means that my function would have to be decreasing, because the derivative is negative. Excuse me. Alright, and then when x is bigger than 2, the derivative goes positive, so we know the function would be increasing. So if we envision in our mind's eye then what the solutions are looking like, when the outputs are below negative 2, the function's increasing, so they will always move up. Now note, if the output is less than 2 and the derivative is positive, that means these solutions will be moving, the function will always be moving up towards negative 2. When you're in between negative 2 and 2, it's negative, so it's decreasing. So the output of the function, once it's inside 2 and negative 2, it's going to decrease down to negative 2. And if it's above 2, the derivative is positive, so the output of the function will increase away from 2. So if we think about that, -2, if you're below -2, your function will increase up towards -2. And if you're above -2, your derivative is negative, so your function will decrease down towards -2. So in this case, we say that -2 is a stable equilibrium solution, because all other solutions nearby get attracted to it. Like exactly what I just said, any solution slightly below -2 has a positive derivative, and thus it's increasing, and any solution slightly above has a negative derivative, so it decreases. And then the opposite is true for 2. If you're a little bit below 2, derivative is negative, so you move away from 2. And if you're a little bit above 2, derivative is positive, so you blow away. Now, to help visualize this, what we can now do is plot something called a slope field. And here it is. So let's break down what this is. So here we have the t-axis, and here we have the x-axis. The x-axis. So t is almost always time in these things, so we never care about when t is negative. We only care about t being positive. So we're almost never going to draw it unless we need to for reasons. And now what is this doing? Well, remember, my differential equation here, x prime, where is it? Okay, is x prime is equal to 4x squared minus 16. So when you plug in an x, you get derivative information, you get slope information. So this axis that I got here, we have the t-axis going horizontally and the x-axis going vertically. So you have coordinates. You've got a t and an x that you can plug in. Now note, t doesn't factor into the differential equation, so it's autonomous. That's why you see if you pick any horizontal line, the slopes are always the same, because t doesn't matter, the x is what matters. But when you plug in an x, you get into the differential equation, you get derivative information. So note when it's 2 or -2, we know the derivatives are 0, so we know it's flat there. So we can plot these out, and this actually gives you a rough picture of what solutions are going to look like. And again, you spent maybe like 20 minutes if you're talking about this. Maybe it was like a whole day you did this. But these are very powerful because they give us information about how the solutions behave without actually computing them. So note here, I have plotted a solution to the FEQ with an initial condition of 0, with an initial condition of x of 0 is 1. Note that, as we said, since the output of the function is above -2 but below 2, its derivative is negative, so it decreases. And so where we see it crushes down to 2. Note that any function whose solution was down here would increase up to -2, and anything above 2 would quickly blow away from 2. So nice and stable there. So this gives us a nice little sampling of the kind of techniques and methods we're going to be employing in the course. As we're going to see, the one-dimensional case is actually incredibly nice because basically this picture right here is usually all you're ever going to get. Which, while that's nice, it is kind of boring. It makes one-dimensional things not worth really studying. We're going to see the real shit when we get to 2D, and then we're going to go bonkers when we go to 3D. As we've already seen. But yeah, this is a nice little taste of the stuff we're going to do in this course. Alright, beautiful. Alright, and let's, like I said, code-wise, so we're going to make computers draw pictures for us. I do this in Sage, which is pretty good. Although I can't get Sage working on my computer right now for some reason, but I can get MATLAB working, and I haven't used MATLAB in a while, so I got all the Sage code from the last time I taught the course, so I gotta convert it over to MATLAB. It shouldn't be too hard, but we'll see. Anyway, so make computers draw pictures for us. It'll be beautiful. Alright, so there we go. Alright, so I'll see you in person on Friday, where we'll investigate this idea a little bit further. And really emphasize why we usually do not care about actually getting a solution. So it's worth noting that this DE isn't too hard to solve. It is separable. It's a partial fractions. It's a little bit of work, but you can solve it. It's some exponentials. It's not difficult. But again, while I have this formula and that's nice, I know everything about this function already just from the equilibrium solutions. I know that as t goes to infinity, this is just going to approach -2. It has to. Its derivative is negative. It's got to be decreasing. right? It's going to go to -2, where it can't go anywhere else. Right. The same thing's true for the other solutions. So, note, I'm able to extract information about my function without actually solving it. And as we saw with Lorenz, you can get some good stuff just from doing that. So, all right. So that is a little sampling of what we're going to do in this course. So we'll see you in person on Friday.